Dr. Mandis here. I just want to talk to you about titrations. Today is titrations. Titrations is a huge amount in general chemistry, and I'm probably going to have a couple of videos on titrations. This is just to say, hey, this is generally what a titration is, okay? And we're going to talk about titrations and move into acid-base titrations. But anyway, if you look up there, I got titrations. It's basically you use something that you know, a known concentration of something, and react it with an unknown concentration of something else. And by the stoichiometry of the reaction, you can calculate the unknown concentration. Typically, of what you got, you put the known concentration in a burette. Our burette is something, it's kind of like a graduated cylinder pipette combo so that you can actually measure the exact volume that you add because you don't know exactly how much you're going to have to add. All right, so you add it in a burette, and then when you go back to it, you can say exactly how much you added. So the known is in the burette, the unknown dude is in the beaker, and you measure his volume ahead of time, and then you can sort of figure everything out at the end. In acid-base titrations, what ends up happening is your base is your known, your acid is your unknown. So down here in the beaker, we have the acid, up here we have the base. Often we could reverse it, but typically a lot of the labs that you do in general chemistry have a known amount of base and you're reacting with an acid. Not always true, just for this example, that's what we're going to do. So basically, I need to show you how you do the math and setup of all this stuff. Using the stoic and unit conversions, you calculate everything. So here's my example. 20 mils of 0.2 molar sodium hydroxide titrated 30 mils of acid. What's the concentration of the acid? First, what's our reaction? Okay, the reaction is the sodium hydroxide with the HCl to produce water and sodium chloride. That's a classic acid-base reaction. Acid plus base makes salt and water. In this case, base plus acid is making water and a salt. But you need to do a little bit better than that. If you're in first year high school chemistry, maybe you get away with that if it's not an honors course. But NaOH and HCl and NaCl aren't really in solution. Don't wig out on me just yet. The NaOH is really sodium and hydroxide because they soluble ionic compound, strong base, dissociates completely. The NaCl is a soluble ionic compound. It dissociates completely. You may be thinking I'm adding complexity. Not even done yet. HCl is a strong acid. Well, it's going to react with the water that it's dissolved in. It'll dissociate completely because it's strong. Am I making things overly complex? Look at this big long reaction I made now. But hey, look, cancel the spectator ions. Sodium cancels sodium. Chloride is canceling chloride. Alrighty, so all you really get is the hydroxide and the hydronium making water, and that's what we have right there. Alrighty, so we got a groovy little hydroxide and the hydronium making water, and that's going to be true of any strong base with any strong acid, not just NaOH and not just HCl, but any strong base with any strong acid. So instead of making it more complex, this reaction makes it actually more simple. But let's look at the math now. How much strong base did we add? Well, this part of the equation deals with the strong base. Volume cancels out, gives you molar of your base, the moles of the base. We need to get to the molarity of the acid, which is moles per liter. So we need to cancel out the moles of hydroxide and get the moles of acid by the 1-to-1 ratio. Then we divide over here by the volume, and we get moles per liter. It gets easier. Okay, let me get rid of some of those reds. It gets easier. If you just look at it, generally speaking, we have, this is the volume of the base here, molarity of the base there. We use the 1-to-1 ratio. 1-to-1 we could probably get rid of because it's just a bunch of ones. If you don't care about the units, I usually do, but for right now I don't. And here we're dividing by the volume of the acid. All right, so that makes a kind of an equation there to get the molarity of the acid, right? That equation I summarized here, and I rearranged it to MBVB equals MAVA. I like that. It kind of sounds like P1V1 equals P2V2. MBVB, MAVA. Sometimes people put the A's first, sometimes B's first. Who cares? All right. Molarity times a volume will get you to a number of moles. So this is moles of the base. A molarity times the volume gets you to the moles. This is moles of the acid. So that 1-to-1 ratio is kind of what we're hinging around. The moles of the base equals the moles of the acid. So we'll just basically, if you ever have to solve for an unknown, you just use that equation. The molarity of the unknown times the volume of the, molarity of the base and the volume of the base, molarity of the acid, volume of the acid. It's easy, okay? Don't make hard out of easy, all right? The only question that we would have is we're assuming up here, way back up here, when I gave this question, that when so much base was added to this volume of acid, that the reaction was done. So we were at the 1-to-1 ratio, so we could use it. Well, how do you know if that's true? That's actually a really good question. What you add is an indicator right here, okay? An indicator is a weak acid that changes color when it deprotonates. They're really big molecules, and the deprotonation causes a shift in the double bonds, and that shift in the double bonds causes it to absorb light differently, which changes the color. I don't really need to know that, but anyway, what I'm saying here is, what if we had a blue HIN, and it becomes yellow when it's deprotonated? Okay, remember your acid-base chemistry. Great to be fluent. When the pH equals the pKa, then your concentration of your acid, in this case the blue, equals concentration of the base, in this case the yellow. And blue and yellow make, happily, green. So back up here, let's explore this little guy right there. Okay, let's go into your experiment. I have some pictograms here. Okay, first, okay, first you're going to have your base in the burette, that's yellow. Okay, it wouldn't really be yellow, but because you wouldn't have the indicator of that, but let's pretend we did. And we added the indicator into the beaker to be blue. So if we added a little bit of sodium hydroxide, we started dripping sodium hydroxide into the acid, the pH would still be acidic because not enough sodium hydroxide has been added yet. But at some point, you're going to get to the perfect point where the moles of sodium hydroxide added are going to be equal to the moles of the HCl. That is called the stoichiometric endpoint, and really I call it the stoichiometric endpoint. A lot of people call it an equivalence point, and pretty much everybody calls it an equivalence point. But right now I'm focusing on that stoichiometry, which is why we're calling it the stoichiometric endpoint, not the equivalence point. But anyway, so you're at this point where everything's done. At that instance, the solution would have turned green because you're at the point of neutrality. So there's no extra base, there's no extra acid. What's causing this is just you're at the pKa of that puppy right there, your indicator. So if you end up in a lab adding a little bit more sodium hydroxide, which a lot of students do, you blow past it and you have to do it again and stop when it's green. Because when it's green, you can measure the volume of the sodium hydroxide that has been added to get to that initial measure of the volume of the acid that you added. And then you can do your MAVA equals MBVB and solve for your molarity of your acid that you're going for. Because now this is known, it was measured in the beaker. This is known, it was measured from the burette. And that was known because it was given to you ahead of time. So that basically is how titration is conducted. I hope you learned something. Like it. Have a good time. I'll talk to you later.